Okay, Bismillahirrahmanirrahim. So last session, we looked at the introduction of halogenoalkanes. So as you all know, halogenoalkanes are functional groups of alkanes. It was derived from alkanes, and one or more hydrogen atoms in the alkanes have been replaced by halogens. Halogens are elements in group 17, your fluorine, chlorine, bromine, iodine. I'm going to skip the part on aquasilver nitrate first, which is on page 2 of your notes. So I would like to move on to question 3. I'll revisit the aquasilver nitrate for later on, because you will need that. You will need to learn the mechanism before you're able to do that. Okay. So the next section that we are going to look at is the production of halogenoalkanes. So how do you produce halogenoalkanes? There are 3 reactions, well, 3 types. Okay. The first 2, the free radical substitution, is something that you have already covered. So halogenoalkanes can be produced from alkanes, obviously, because it is a derivative of alkanes. Halogenoalkanes can also be produced from the electrophilic addition of alkenes. You've also seen this reaction. And the last one is something that you have not seen, which will be the only thing that's new for you. Okay, substitution of an alcohol. So these are the 3 types of reactions that can be used to produce halogenoalkanes. We know that free radical substitution is not a great reaction if you want to produce one type of halogenoalkanes, because it is a chain reaction. You can get a mixture of products. So if you are given a choice to choose out of these 3 reactions, which one, in order to produce a desired halogenoalkane, one type of halogenoalkane, you would go for reaction number 2 or reaction number 3. At least these reactions, they don't have side products. The reaction is not continuous. Once you get your desired product, the reaction should stop. Okay, so just to recall this, you don't have to copy down the mechanism, because it's something that you have covered in topic 14 already, the previous topic. It's called the free radical substitution of alkanes. So what happens is that your hydrogen in your alkanes will be substituted with a halogen. So in this case, a hydrogen atom has been replaced by a chlorine atom. So because radicals are reactive species, it doesn't just stop there. It will continue to react until all the hydrogen atoms have been replaced by the chlorine atom. Okay. The second type of reaction is something that you have learned as well. It is called the electrophilic addition. In your notes, you are given the first example where you use hydrogen halides. Okay, so HX in the notes means it's a hydrogen halogen. X is representing a general halogen, whether it's chlorine or bromine. So the hydrogen, the halogen halides will be added across the double bond. So one bond will be added to the first carbon of the double bond. That's where your hydrogen goes in first. And then the second carbon in the double bond will be forming a new bond with your halogen X. So that is the general mechanism for halogen halides with alkenes. Okay, if you react your alkenes with halogens, for example, Cl2 or Br2, you are adding 2 halogen atoms across the double bond, with one atom attached to each carbon. Okay, so if you only want to attach one halogen, you will use halogen halides HX. If you want to attach two halogens, you will use the element in its standard state, whether Cl2 or Br2. Now, please remember that these halogens will only be added across the double bond, not any other carbon. Okay, it's only attached to the functional groups of your alkenes. So if you have an alkenes with, say, 20 carbon atoms, the only reactive site of that alkenes is where your double bond is. The rest of the molecule will just stay inert. Okay, so that's the reaction of your alkenes with either halogen halides or with halogens. Okay, so if you could just label this in your notes where you have this diagram. Okay, so HX is called a halogen halides, right? The halides stands for the hydrogen, the H, and the halogen is the X. Okay, so there's no special condition for this reaction. You just need room temperature and you leave it to react. So that's how reactive alkenes are compared to alkanes. So this reaction of alkenes can also happen in a dark room. Right, the third reaction is something new for you, which you have to learn in this topic and the following topic when we come to cover alcohols. Okay, so your alcohols can be transformed into a halogenoalkane in what we call a substitution reaction. Okay, so what happens is that your hydroxy group, OH, will be substituted with the halogen in your halogen halides. Same thing, you can react your alcohol with the halogen halides, but there is a condition. You need to use you need to use a potassium bromide or a sodium bromide with a catalyst, sulfuric acid or phosphoric acid. So halogen halides is not something that you can produce beforehand and then you keep it in a bottle. No. Halogen halides can only be produced inside the reaction. We call this in situ. Okay, that means on the spot. It is produced on the spot inside the reaction mixture in the same apparatus where you would have this reaction happening. Okay, so you would add potassium bromide or sodium bromide. Okay, anything of the group 1 metal bromide as long as the bromide is there, and then you need an acid catalyst, whether it's sulfuric acid or a phosphoric acid. So what happens first is actually potassium bromide will react with the sulfuric acid to form the halogen halides. So in this case, is the hydrogen bromide, for example, HBr. Okay, and then the reaction will happen where your halogen atom will replace the hydroxy group in your alcohol. Okay, so that's where you see your halogens end up, and the other product is water. That's one type of reaction with alcohols. If you don't want to use potassium bromide or sodium bromide with sulfuric acid, you can use PCl3. Okay, so this is called a phosphorus trichloride. So phosphorus trichloride can be obtained readily. Okay, phosphorus trichloride. So this reaction is straightforward. You just throw in PCl3 and then you heat it. And same thing happens. Your hydroxy group is being replaced by one chlorine atom. Okay, even though there are 3 chlorine atoms in PCl3, but only one chlorine atom will be added or substituted. Okay, why? Because you don't have any other OH group. The rest are just hydrogen bonds. You cannot, the chlorine cannot kick out the hydrogen bonds. The only thing that the chlorine can kick out is the OH group. Now, if there's more than one OH group, then of course that's a different story. Okay, the chlorine will replace both the OH groups. So it all depends on the hydroxy group. That's your functional group. We're not interested in the CH bonds. They stay inert. The other product would be phosphorus acid. Okay, so this is different from phosphoric acid. This is called the phosphorus acid. Another type is if you don't want to involve heating, you use a PCl5. That's called the phosphorus pentachloride. Halogen halides. No, sorry. Yes. Halogen halides and hydrogen halides. Yes, you're right. It's hydrogen halides. Sorry. Yes. It's not halogen halides. Thank you. It's hydrogen halides. So thank you for correcting me, Nina. It should be hydrogen halides. Okay. So the halides is actually for halogens. Okay. So that's my mistake. Thank you for correcting me. Okay, moving on. So please change that. It should be a hydrogen halides. Hydrogen halides. And the halides is for the halogens, not the hydrogen, okay? Okay, moving on to reaction, the third type of reaction of alcohol, if you want to use phosphorus pentachloride, okay? Again, PCl5 is readily available. You can just add it to an alcohol and it reacts at room temperature, okay? So when it comes to a reaction, usually we want to use a reaction that is that reacts easily, spontaneously. It doesn't require a catalyst. Even better if you don't need to heat it up. Okay, so PCl5 is a good reaction to produce a halogenoalkanes. Another type of reaction is SOCl2. Okay, we call this SOCl2. There's a scientific name for this, but I will explain that to you in the next topic. Okay, so same thing, SOCl2, SOCl2, that's not the scientific name. Okay, same thing also, the hydroxy group is being substituted with your halogens. The other product would be hydrogen chloride in the form of gas, okay, and sulfur dioxide, which is also in the form of gas. So in topic 16, you will actually observe white fumes for this reaction, okay? And this reaction, because it's something that has an observation, it can be used as a test, okay? A test for the presence of hydroxy group, right? But for now, I will just leave it at that. Okay, so these are the reactions that you can use to produce halogenoalkanes, the desired halogenoalkanes. Okay, right. Moving on to the reactions of halogenoalkanes. Okay, so halogenoalkanes as you saw from the previous slides, halogenoalkanes can be formed in a substitution reaction. Okay, and because halogenoalkanes contain single bonds only, we say that halogenoalkanes are saturated, just like your alkanes. They all contain single bonds. They are fully saturated. So when it is involved in a reaction, you can only substitute the bond. You cannot add any more additional bonds, but what you can do is substitute, replace your original atom with a new atom. Okay, so the reaction for halogenoalkanes, well, one of them is the substitution reaction. Okay, halogenoalkanes will also undergo an elimination reaction, which we will visit later on. Okay, so in your learning objective, it mentions SN1 and SN2 mechanism. So that's the name of the mechanism. That's the type of the mechanism. Nucleophilic substitution. For alkenes, you have come across electrophilic addition. So for halogenoalkanes, you have to memorize that it's nucleophilic substitution. Okay, and then it says that primary halogenoalkanes will react via SN2, tertiary halogenoalkanes will react via SN1. Okay, so before I talk about that, I have to teach you the SN1 and SN2 mechanism first. Okay, so now we're looking at reactions of halogenoalkanes. So halogenoalkanes undergo the nucleophilic substitution reaction. So the name of the mechanism is nucleophilic substitution. Just to introduce to you the concept of nucleophiles. Nucleophiles are electron pair donors. So species with electron pairs can act as nucleophile. You saw in the previous topic that alkenes, the C double bond C, which is rich in electron, they act as a nucleophile because they can give away their electron pair. Okay, so some of the example of a nucleophile here is the hydroxide ion, OH minus ion. There's a lone pair on the oxygen, so it can act as a nucleophile. Ammonia, even though it's not charged, but there is a lone pair on nitrogen. CN is called a cyanide ion. Okay, cyanide ion is a CN with a negative charge, and the lone pair is on the carbon. So students always make this mistake of thinking that the double bond belongs to the nitrogen. Okay, so actually the the lone pair of electron belongs to the carbon, not the nitrogen. Water can act as a nucleophile as well because it has a lone pair on oxygen. Why is it important to locate their lone pair of electrons? Because whoever owns the lone pair of electron, and when it donates, that is the point of attachment when you are making a new bond. Okay, so if carbon is donating the electrons, the new bond will be formed with carbon, not with nitrogen. Okay, so same thing, if oxygen in H2O is donating its electrons, a pair of electrons, the new bond will be formed between the oxygen and whatever atom that it is donating the electron pair to. Substitution, definition of substitution, well, halogen atom is being swapped with another atom or groups of atoms. Okay, there are two types of mechanisms. SN1 is for tertiary halogenoalkanes, SN2 for primary halogenoalkanes. So what about secondary? Because secondary is in the middle, so it can go via as both SN1 and SN2. So that means it will be a mixture. Okay. Right. Let's talk about the theory first. Okay, before we look at the mechanism, we want to look at a halogenoalkane. Okay, so if I just draw a general halogenoalkane, for example, chlorine. So this is a chloropropane. Okay. Now for a chloropropane, the only reactive part is the functional group, which is the carbon-chlorine bond. Everything else, the carbon-hydrogen, the carbon-carbon bond, they will stay inert. So my focus should only be on the carbon-chlorine bond. Now, as you can see, carbon and chlorine or any other halogens, there will be a difference in electronegativity values. As you know, chlorine is one of the highly well, not highly, but the electronegativity is relatively high. So chlorine will develop a partial charge, which is delta minus, and carbon will develop a positive charge, delta plus. Okay. So this carbon-chlorine bond is a polar bond. It's something that we know already. Okay. So what happens when you have a nucleophile with a lone pair of electrons? This nucleophile may be negatively charged or neutral. Okay, as long as they have that lone pair of electrons. So a nucleophile is usually an electron-rich species. So electron-rich species will attract electron-poor species. So between delta plus and delta minus, obviously delta plus is electron-poor. Delta minus means it has a high electron density. Delta plus means it has a low electron density. Okay, so this nucleophile will attack the slightly positive carbon, or we say the electron poor region of the molecule. Okay, so that's what's going to happen. The slightly positive carbon, the one with the delta plus, is then open to be attacked by nucleophiles. Okay, right. So let's go straight to SN1. Okay, so sorry, SN2. We're going to look at SN2 first because that is the easier. Not necessarily. Okay, so what happens is we're going to use a primary halogenoalkane. An example, bromo, just a simple bromoethane. Okay, so this is where you should start copying down. Okay, so that's a bromoethane. And the nucleophile is hydroxy. OH minus. And the lone pair is on oxygen. It is important that the lone pair is on oxygen. Before this attack can happen, you need to draw the dipoles. Without the dipoles, the reaction will not happen. Okay, you cannot have a lone pair of electrons attacking a normal carbon who is not electron poor. Otherwise, they will just repel. Okay, because we would imagine this carbon, the one that has no dipole, will be having some sort of electron density. Okay, here at least we know that, oh, delta plus means that it has low electron density. Delta minus means it has high electron density. Okay, so what happens is that the lone pair of electrons from the hydroxy ion, OH minus, which is your nucleophile, will be donated to the carbon. Okay, so you would imagine oxygen will form a new bond with carbon. Carbon will now have 5 bonds. So something needs to be broken. And the bond that is broken is usually the weaker bond. Okay, the CH bond will not be broken, right? Sorry, the CH bond here will not be broken. This carbon-carbon bond will not be broken. It is the carbon-bromine bond. Plus, bromine has a higher electronegativity. That means they have an attraction, a strong attraction towards the electrons in this green bond. Okay, so because carbon is now forming 5 bonds, so then the CBr bond will break and the electrons will go to bromine. Okay, so what happens next is that we have a what we call a transition state, just like your intermediate. Okay, a transition state looks like this. Because it is transition or intermediate, that means it is in the process. Okay, so the bond being formed is in the process of being formed, and the bond being broken is in the process of being broken. So we write this. You will sometimes see that symbol where it represents transition state. Okay, so this transition state is like a short-lived species. Okay, they don't exist very long. They are just there for a short time. Okay. Next is then your product. Okay, so as I said, okay, before I go on to the product, this is bond forming. It is about to form, and this is bond breaking. Okay, the bond is about to break. And then you get to your product where you have the carbon hydroxy bond. This is the newly formed carbon. Everything else, the rest of the molecule stays the same. Okay, don't forget your other products, which is from here. When bromine gets the electrons, bromine now becomes bromide plus Br minus full negative charge. Okay, it has to become a full negative charge now because it already has the lone pair of electrons. It owns the lone pair of electrons now. Okay, for the explanation, is there an explanation for this? Yes, there is an explanation. Where can I get the explanation for that? Okay, so after you copy this down, I will show you the next slide for you to copy down the explanation. Okay, so this is the explanation. So you can see here the attack is coming from the other side. Yeah, I forgot to mention that. The nucleophile attacked from the other side of the halogens. The reason is because they want to avoid repulsion, right? So here I don't show that to you, okay? But in reality, it attacks from the other side. This is called the inversion. Okay, so if you want to copy, you can copy this down. So you will notice that sometimes the diagram will write the negative charge of the hydroxy group in a bracket, or you write it on the hydroxy group itself. Okay, it doesn't matter as long as you don't drop the negative charge. Okay, so I'll let you copy this because there's about 5 minutes left. In the meantime, do you have any question?
No.
Okay, so I'll just let you finish copy this.
Excuse me, Miss.
Yes.
Hello, our exams. Do we have to do? You have to do the diagram in 3D.
It depends on the question. Okay, if it doesn't require for the 3D product, then you don't have to. You just draw like normal bonds, like I have drawn it here, seen it, okay? But Ani, this dotted is not 3D drawing, that is just showing you that the bond is on the way to be broken and on the way to be formed. Okay, so this is not a 3D drawing. This one is just showing you extra information. The reason for this is because they want to show that whenever these attacks happen, the nucleophile will attack from the back on the opposite side of where your halogen was. Okay, so that's why there's a change in shape there. They draw the 3D drawing so that you can see where the attack is coming from, which is the opposite side. Okay, so I can add that on. Attack of nucleophile from the opposite side. Okay, so